Hello everyone, today I want to review the filament buffer system for the Palette 2 and Palette 2 Pro. The filament buffer is a very essential component of the Palette 2. It pretty much defines the overall speed of the machine. It's easy to think that the splice core is the most important component in that regard, and it sure is important, but its performance is more tied to the laws of physics and not as easily tweaked as the buffer system, and it has less impact on the actual printing speed than you might think. Another very essential factor for the overall speed is of course how the firmware and other surrounding software controls the print process. And here Mosaic have only implemented the absolutely bare minimum required for the system to work, with no focus on optimizing performance. And this bare minimum is so saturated with very serious bugs that you can hardly say that it is functional. When I have talked with Mosaic about improving performance, the only thing they seem to focus on is splicing performance, which I find very strange. It looks like the impact of both the buffer system and the firmware have been pretty much neglected, and all focus has been on splicing. As a video game programmer, I draw some parallels to a mistake many programmers do when optimizing. They spend a ton of time optimizing some very inefficient part of the code, maybe getting it tens or even hundreds of times faster. Then they find that all their effort hardly made any difference at all, because the now highly optimized and often completely unmaintainable piece of code was run so rarely that it only accounted for like 0.5% of the total runtime. But let's get started. Here you see the front of the Palette 2 with the acrylic cover over the buffer removed. The buffer is being fed by the output drive here, and the printer pulls the filament out via the scroll wheel here. The scroll wheel measures how much filament the printer have used. In the center there is a switch that is used to detect when the buffer is empty. Here you can see how the buffer decouples filament production from filament consumption. When the Palette 2 have to stop feeding filament into the buffer during splicing, the printer can keep pulling filament from the buffer. So how much filament can the buffer hold?
The buffer, which is now built into Palette 2, will hold 12.5, so 125 millimeters of filament.
So according to Mosaic, it should hold 125 mm of filament. Let's go ahead and measure it. We load enough filament that some is sticking out even when the buffer is full. Then we mark the exit point on the filament. Now we pull as much filament as possible out of the buffer to make sure it is empty, and cut it flush with the output. We then cut it at the mark we made and are left with a piece of filament that represents the total size of the buffer. We then straighten the piece a bit and measure its length. And as you can see, the total size of the buffer is actually 125 mm. It has become crystal clear to me that you should never trust anything coming from Mosaic. But this time they were actually telling the truth. But is this enough buffer to keep the printer happy during splices? According to the CEO of Mosaic, it is.
There's 12.5 centimeters worth of expansion and contraction. There's some really fancy math that goes along with this that the team has explained before, but because the minimum piece length in Palette 2 is 8 centimeters, 12 is actually more than we need. And in fact, making the buffer bigger won't lead to faster printing. I know that's a bit counterintuitive, but they found that having, I think it was anywhere over 10 centimeters is more than enough that we need to make sure that Palette 2 can generate filament at its own rate in the printer, but keep up to the average print speed of the printer for most speeds.
As you heard, he claims that anything about 10 centimeters is more than enough. So with a 125 mm buffer, that should be plenty. But is the palette actually able to utilize 100% of the buffer? Let's get it going in multispool mode and see how much filament it actually keeps in the buffer. First we slowly pull out enough filament to get it through its first pong, where it calibrates itself. Then we pull slowly on the filament as the buffer fills to mimic a printer. Then we keep slowly pulling out filament. Now the palette will let the buffer drain a little, and then add some filament, let it drain a bit again, and then add more, and so on. We will now try to find the lowest point the buffer is at before it is being refilled. Then we turn the palette off to prevent it from filling any more filament into the buffer. Then we mark the point where the filament exits the palette to. Then we pull as much filament as possible out of the buffer and cut it flush with the output. Then we cut it at the mark we made earlier. Now we have a piece of filament that represents the actual amount of filament that the Palette 2 keeps as a reserve during printing. So let's straighten it a bit and measure it. (49 mm). So the actual buffer utilization is 39.2%. It seems like it varies a little bit. I've previously measured it to like about 52 mm, but that was using a slightly less accurate method, so it might have been measurement error, or the actual utilization might vary a bit. But this time it was clearly 49 mm, so I'm going with that for the rest of this review. This is even less than the 10 centimeters the CEO claimed would be enough for everyone. This is not the whole story when it comes to how much filament is available during a splice though. The splice starts by cutting the filament and then move the outgoing side of the cut filament into the splice zone. The distance between the cutter and the splice zone is 33 mm. So whenever the splice is started, 33 mm extra filament is added to the buffer. Since we start with 49 mm filament available in the buffer before the splice and 33 mm is added when the splice starts, we have a total of 82 mm available during the splice, or an efficient buffer utilization of 65.6%. Still not at the 10 cm mark. So what does this mean for the speed that we can print at? How fast can we print before we risk having a buffer underrun and a failed print? Let's first listen to what their CEO have to say about the matter.
In terms of speed, this is actually a really hairy thing. We've been working a lot this week, in fact, and we're going to try and put together some type of blog post to communicate this clearly. But when you talk about speed, it's kind of the Wild West when it comes to 3D printing. The reason being that, first of all, there's multiple slicers. A lot of them define speed in terms of the feed rate, the travel rate of your print head. So we're trying to figure out volumetric consumption of filament based on the speed that your print head is moving. And then there's multipliers on that. So say your base speed is 100 millimeters per second. If you're doing infill, that's going to be a different speed than perimeters. The layer height is going to affect the amount of volume that's used per pass. So there's a lot of ambiguity out there when people say a printer prints at this speed. We want to make sure it's really clear. We want to help people understand if Palette 2 or Palette 2 Pro is right for them based on speeds, as well as what some of the limitations and new features of Palette 2 are going to be. So I don't want to completely not give any answer to this question, but it's a really challenging one to explain. What I can tell you is that this Maker Gear print right now is printing at 50 millimeters a second, and the Palette 2 itself is keeping up completely fine with that. I believe we could go faster than that. I don't know exactly what the max speed would be, but what we want to do ideally with this blog post is help you understand, based on your slicing settings, what an equivalent filament consumption rate would be that you can then compare to the filament generation rate of Palette. I know that was a lot of information and a lot of terms. Does that kind of make sense, Brennan?
I think it does.
This is what it sounds like when someone don't want to tell you something, but don't want to tell you that they don't want to tell you. Is speed really as hairy as Mitch tried to make it sound like? Of course, slicers specify the speed in terms of travel rate of your printhead, but converting travel rate to volumetric consumption when you know the nozzle diameter and layer height is very trivial. Mitch probably knows this, but throws in as much technical mumbo-jumbo as possible as a smokescreen. Cross-section of a 1.75mm filament is calculated like this. I'm going to assume 0.4mm nozzle and 0.2mm layers for all calculation in the review, unless otherwise noted. And then the cross-section of a single stripe on the print is calculated like this. Note that the cross-section of the plastic strip laid down is not the same as the cross-section of the 0.4mm hole in the nozzle. The nozzle will extrude enough plastic to make a solid 0.4mm wide and 0.2mm tall strip of plastic that is nearly square. not a 0.4mm round rod. With that knowledge, it is trivial to calculate the ratio between consumed filament and millimeters of head travel. So we consume about 1mm of filament for every 30mm of head travel. If we in addition know how long the Palette 2 used to splice filament and how much filament is stored in the buffer, we can calculate the max speed the printer can move the head at without depleting the buffer before the splice is done. By frame stepping a recording, I found that the default PLA to PLA splice profile takes 39 seconds from cutting the filament till it's done splicing. And we have already determined that there is a total of 82mm of filament available during a splice. 82mm of filament will give 2465mm of extrusion. If we then divide that on the 39 seconds it takes to splice, we get a maximum average printing speed during a splice of 63mm per second. As you can see on this page, Mosaic claimed that recommended maximum print speed for PLA is 63 to 103mm per second for the non-pro, which is curious. When looking at the first number, it almost looks like the engineers at Mosaic actually owns a calculator and knows how it works. But where did the 103 come from? And how do you decide which one to use? Another definition of the Palette 2 speed is here. I wonder if that is the blog post Mitch was talking about. I guess not, but I've never seen that blog post anywhere else, so I'm just curious. But anyway, here they define just a single speed, which makes more sense. More about that later, but the way they define it is really odd. Everywhere else they use millimeters per second, so why do they use millimeters per minute here? And elsewhere they use 0.2mm layers, while here they use 0.3mm. It is almost like they want to show the numbers but not have people realize what they mean. But let's convert them to the most common format and the format that we've used in the rest of the equations here. First, to convert from millimeter per minute to millimeter per second, we simply divide by 60. So that gives a travel speed of 90mm per second. But we also have to convert from 0.3mm to 0.2mm layers. The printer will extrude less filament per millimeter when using 0.2mm layers. So the equivalent speed that will give the same filament flow will be 135mm per second. Well, that is a problem. We just calculated that the maximum speed will be 63mm per second. So where did this number come from? Let's start by calculating how much buffer is needed to prevent it from running out during a splice. Maybe whoever calculated that number assumed that it would be able to utilize the full 125mm of buffer capacity. So to prevent the buffer from running out during a 39-second splice, we need 175mm of buffered filament. Now that is a serious problem. The total buffer is only 125mm. Remember I mentioned that you should never trust anything coming from Mosaic? Well, here is why. Pretty much everything they claim is pure fabrications. I don't believe I've ever in my whole life dealt with another company that is so consistent in lying about its performance data, and to such an extreme degree. I have no idea whose ass they are pulling their numbers out of, but I know it's not a very accurate one. The speeds we have been dealing with here is of course average speeds during a splice. The multipliers that Mitch mentioned, and acceleration and deceleration that he didn't mention, is of course complicating things a bit, but as demonstrated now, there is nothing hairy about converting between speeds and volumetric consumption. And there is no ambiguity in the calculations, they're 100% objective. That does not mean that they yield numbers that you can plot directly into your slicer and be guaranteed to run at peak performance while never experience a buffer underrun. If, for example, all your multipliers are 100% or less, and you use 63mm per second as your base speed, you should have been pretty safe. Time spent accelerating and decelerating will only reduce the average speed and give you better margins, and unfortunately that is not the case. Not because there is any ambiguity in the calculations, or because 63mm per second is an entirely made up bluff like Mosaic's numbers, but because the buffer system in the Palette 2 is so unpredictable. Sometimes it will mess up the coordination between pongs and splices, and then you suddenly have cases where it have much less than the 49mm we measured available in the buffer when the splice starts, and the maximum safe speed drops accordingly. This part is entirely unpredictable and makes finding a safe speed really hairy, but not at all for the reasons that Mitch tried to make us believe, but because of massive design flaws in the Palette 2 buffer system. It should be clear by now that Mitch's comment about 10 cm is complete bullshit. It have no bearing in reality at all. If you have a print where all splices was the minimum length of 8 centimeters, then sure, average and worst case is the same and there is nothing the buffer can do to smooth things out. But usually you have much more than 8 centimeter filament times the number of colors in each layer, and then the buffer can average out the consumption over the whole layer. The minimum buffer needed to utilize the splice core at 100% of its capacity is dependent on the total amount of filament per layer and the splice type. It has nothing to do with the minimum piece length that the palette can produce. And we can also easily conclude that even if we were able to utilize the full 125mm of the buffer, that would in no way be enough to reach the speeds that Mosaic claims the palette should be capable of. But why are we not able to use the whole buffer? That is because of the way Mosaic have designed the buffer system. The buffer system consists of 4 main components. First it is the drive that pushes filament into the buffer, then it is the buffer space itself, then it's the scroll wheel that measures how much filament that exits the buffer, and last it is the switch that detects when the buffer is empty. Since the drive filling the buffer uses stepper motor, they can control pretty accurately how much is pushed into the buffer. And with the scroll wheel, they can measure pretty accurately how much filament is being pulled out of it. In theory, when the print starts, they can just fill the buffer to 100% minus a bit of space for printer attraction and the 33mm that is added during splicing, and then simply continue to refill the buffer with the exact same amount that is being pulled out of it, and it would stay at a constant perfect fill level. Unfortunately, theory and practice is only the same in theory. In the real world, there will be some amount of slippage on the filament drive, and that will lead to less filament being driven into the buffer than the palette to account for, and eventually the buffer will drift towards empty. Similarly, there will be some slippage in the scroll wheel, and that will lead the palette to think less filament have been pulled out of the buffer than they actually have, and that will lead to the buffer drifting towards overfill. And there can of course be other sources to inaccuracies too. The end result is that without some additional measures, the optimal buffer level would not be maintained for long. And this is where Mosaic made an almost unbelievable mistake that completely ruins the whole buffer system. The way they decided to solve the drifting problem was by adding a switch that will be pressed when the buffer is empty. This works perfectly fine for calibrating away the discrepancy between the estimated amount of filament being pushed in versus the measured amount being pulled out. Just periodically drain the buffer until the switch is pressed and then fill it back to the desired level. This is what they call a pong. If the period is short enough that the drift between pongs will be negligible, that will keep the buffer at the desired level over any length of time, except for during the pongs. And that is where the devil hides. Having to periodically drain the buffer empty is of course asking for trouble. If the printer runs at the max speed the buffer can support, it is left vulnerable during the whole time the pong takes to complete. In normal multi-material mode, it knows exactly when the splice will come, and it can plan the pongs so they don't collide with the splices. But unfortunately it does not manage to do so, and that will cause prints to fail at random. I'm not 100% sure what the mechanism behind those failures are, but I have a suspicion that if you get a series of splices that is close enough that the buffer will never fill completely up, it eventually just throws in a pong anyway, and voila, buffer underrun, and you have a failed print. These failures are very random and thus hard to analyze, so by guessing around what actually happens might very well be wrong. But I have seen them happen many times, one of them on the Mosaic live stream I have showed snippets from today already. The mishaps in multi-material mode might be possible to fix in software, but the issues this design causes from Multispool mode cannot be fixed. Multispool is a really nice Palette 2 feature that is supposed to make it possible to spend multiple spools of the same material or color on a single print. When the Palette 2 detects that the spool runs out, it automatically splices to the next. That is a really useful thing, and one of the major points on my Pro side when I was deciding whether I should order the Palette 2 or not. No more stacks of almost empty spools that is too short to start to print with. But what happens when the spool runs out right as the Palette 2 have drained the buffer to recalibrate itself? It cannot know in advance when a spool will run out, so it has no way of protecting itself from ending up in that situation. It boggles my mind that the engineers at Mosaic didn't realize that this was never going to work. How is it possible to design a buffer system that has to periodically drain itself in a system that has no knowledge of when the buffer will be needed? That is so stupid that there really can be no valid excuse for it. That, along with the design flaw in the filament input path, as well as several other very serious issues, leads me to conclude that the engineers at Mosaic is entirely incompetent and not at all able to think a problem through before starting to hack together a solution for it. Because of the 33mm of filament that is being pushed into the buffer when a splice starts, this flaw does not render Multispool 100% useless. It will always have those 33mm to work with, but it limits the maximum safe speed to 25mm per second, so still pretty useless. Then it is of course the input section design that I discussed in another video, which roughly guarantees that Multispool remains 100% useless. So how could this problem with calibration be solved without ruining the functionality of the buffer in the process? Well, if they had implemented a detector that would trigger when the buffer was at the max usable capacity or more, that would have enabled them to keep track of the actual buffer level without having to periodically drain it. This would be a bit harder to solve than the buffer empty detector. First of all, the only thing that will limit the force that can be applied to the buffer empty switch is the traction of the extruders in either end of the filament and the tensile strength of the filament. So pushing a button is no problem. Yet in the Palette 2 it turns out that pushing the button actually is a problem. They did not only choose the wrong sensor topology, they also picked a type of switch that is entirely unfit for the job. I'm probably going to discuss that more later. But in general, it's very easy to detect that the buffer is empty. The alternative is a bit harder for a couple of reasons. First of all, it's useless to detect when the buffer is 100% full. Then it would have no space for retractions from the printer or for the 33mm that will be pushed into it when the splice starts. So the detector must detect when the buffer have reached some arbitrary level. Probably something like 125mm minus 43mm, which would be 82mm. This would give room for the 33mm added during splice and 10mm for printer retractions. Detecting a range above some arbitrary level is inherently more difficult than detecting either of the extremes. And if using a physical switch, it would have to be one with very little activation force. If you are printing with flexible filament, you cannot disturb it much before it would bulge instead of pushing the switch. So they might have been forced to use some kind of optical detection. And since the filament isn't always following a perfect arc through the buffer, they would have to detect it at multiple locations to probably estimate the actual fill level. Or even go a route similar to my external buffer that keeps a little tension on the filament all the time. Then it's easy to measure the buffer level by the movement of whatever makes the tension. In the case of my external buffer, that would be determined by measuring the angle of the center spindle. But no matter what route they had taken, this kind of detection had many more technical challenges than a simple buffer empty switch. Those challenges are in no way an acceptable excuse for simply throwing in the towel and picking a solution that is 100% guaranteed to never work. Yet that is exactly what the engineers at Mosaic did. With the detector flagging when the max usable buffer level was reached, they could have kept the buffer at the perfect fill level during all situations and always been able to guarantee that there would be filament available for splices as long as the printer was not exceeding the max supportable speed, a speed now dictated only by the total buffer set. And with the right kind of detection, they could probably have ditched the scroll wheel as well and simply used the combination of current fill level and the number of steps on the filament drive stepper motor to measure how much filament the printer had pulled. And there would be no pongs, just a continuous fine-grained adjustment of the current buffer level. Let's take a look at some practical examples of what problems the current buffer design causes. First we check what happens when printing in multispool mode and a spool runs out at the middle of a pong. To provoke this situation, we will start a multispool print and let it run through the first slow layers and a couple of pongs, so it have established a stable state and is in good calibration. Then we will wait until a pong start before cutting the filament flush with the input. Since there is about 14mm of filament left from the cut till the point where the filament detector trigger, this will not be a worst case situation. In the simulated case, we will have 33 plus 14mm or 47mm filament available for the splice. In a real world worst case situation, where the filament stops right before the trigger point when a pong starts, there will be only 33mm available, or about 70% of what we have in this test. So if the print failed during this test, it would fail even worse in a real world situation where the spool ran out at the most critical time. The object we will be printing is a 160mm diameter cylinder being printed in race mode at 63mm per second. This is the speed we have calculated to be the maximum speed for the PLA on a non-pro Palette 2, and also the absolute lowest end of the speeds Mosaic claim it should be capable of. Now we've got the print running. It has been through the first two layers that is printed at a lower speed, and the Palette 2 have been through a couple of its pong routines. What was displayed on the phone was the requested and the actual printing speed from the printer's web interface. Max speed means the highest speed that was reached during the short period since the last update. For this object, it stays pegged at 63 mm per second for the whole print, except for the first two slow layers. Now it is getting time to cut the filament to simulate the spool runout. When the next pong starts, I will cut the filament flush with the input. There it started the pong. Let's cut the filament and wait for the pong to end. When the pong finishes, it will pull about 14 mm filament into the buffer before the runout detection trigger, and it will have to start a splice. There it finished the pong and pulled the about 14 mm filament between the cut and the runout detection position into the buffer before it initiated the splice by cutting the filament and push another 33 mm into the buffer. Now let's wait and see what happens to the buffer during the splice. And there the buffer ran out. And now let's do the started grinding. So even at the claimed minimum speed, that is only 47% of the claimed maximum speed, the print failed. And this was when the runout happened 14 mm after the pong finished, not right as it ended, which would have been the worst case situation. Now let's test another scenario. This time we are also printing in multispool mode, but this time we will provoke a spool runout right after a pong finished. So that should give the Palette 2 the best possible chance of succeeding. But instead of 63 mm per second, we will print at 80 mm. That is a number I've heard thrown around a lot. And one time I discussed the performance issues with Mosaic, they dismissed all of my arguments and calculations by pointing to a customer that claimed he was printing at 80 mm per second in multispool mode. Just like last time, we have started the print and let it run through the first couple of layers and a few pongs, but as you can see we are now printing at 80 mm per second. We are now ready to provoke a spool runout. When the next pong finished and the buffer is at its normal fill level, we will cut the filament and see what happens. There it detected the runout and started to splice in the next spool. Let's now keep an eye on the buffer and see if the Palette 2 is capable of supporting 80 mm per second under best case scenarios. And there it ran out during a splice again. 45 seconds before the splice had finished, the buffer was empty. Not as bad as in the previous test, but enough to fail the print. In this particular case, it seems like the flexing of the feeding tube saved our ass, but that is not something you want to rely on. And that is probably what saved that customer that was printing at 80 mm per second as well. As long as he stayed lucky enough that all his runouts happen between pongs and there is enough flex in his feeding tubes to make up for the insufficient buffer size, it will work out. But one day it runs out in the middle of a pong, or there is a splice between the palette and the printer that snaps during the tug of war between the printer and the palette that happens when the buffer runs out, then he will have a failed print. Let's hope we use multispool mode to finish an almost empty spool when that happens, and not to be able to make a print that actually needed more than one full spool. Now let's do some tests in pattern mode. Some time ago there was a customer on Facebook that asked how fast he would be able to print in random waste mode and still have the buffer keep up. And Mosaic then replied by linking to the insane page that say that the Palette 2 supports 5400 mm per minute with 0.3 mm layers. So let's try that and see what happens. Now we have started a 2-color print in pattern mode with 30 cm splice length for both colors. The object we print is the same as in the previous tests, but it have been resliced to print with 0.3 mm layers at 90 mm per second, or 5400 mm per minute, to use the same convention as in the document. Let's skip forward enough that it have finished the first slow layers and have to tackle its first splice at full speed. Now it is at layer 3, which is the first to run at full speed, in other words at 90 mm per second. Let's keep an eye on the buffer the next time it needs to make a splice. As you can both see and hear, that did not work out very well. This print failed completely and I aborted it after a couple of splices. Here is what the end result looked like. When I saw this thread on Facebook and the reply Mosaic gave, I was pretty frustrated. It should be obvious to anyone with at least one working brain cell that the advice Mosaic gave was utterly insane, and that the customer would end up with a mess if he tried to follow it. So I replied to their post with math that showed the insanity of the claims made on that webpage, and asked why the numbers looked entirely fabricated without any root in reality. And Mosaic simply ignored it. And they still claim the Palette 2 can support 5400 mm per minute at 0.3 mm layer, and that the Pro version can do 20% more than that. Like I said earlier, I don't think I've ever encountered another company that is flat out lying about its product's performance to such an extreme degree that Mosaic does. Let's do one more test. Remember that the CEO at Mosaic claimed that 10 cm buffer was more than enough, and that anything larger would not make printing any faster. Now we're gonna run the exact same test as the last time, but with 28 cm worth of external buffer connected to the palette. According to Mitch, that will not make it able to print any faster. Here we have got the print through the first slow layers. It is now printing at 90 mm per second and have just started its first splice after reaching full speed. Let's see if the extra buffer space is a complete waste like Mitch claimed. There the internal buffer ran out, just like in the previous test, but this time the external buffer steps in and keeps the printer happy, for now at least. And there, after having drained the external buffer down to about 50%, the splice finally finished. And both buffers are being refilled and ready for the next splice. Let's wait for one more splice to see that it is able to properly recover between splices. Now it started to splice again. And there the internal buffer ran out. Now the splice finished and both buffers fills up again. And the rest of the print continues just like that. And in the end, the result looks like this. Remember what the result with only the internal buffer looked like?
In fact, making the buffer bigger won't lead to faster printing. I know that's a bit counterintuitive, but they found that having, I think it was anywhere over 10 centimeters is more than enough that we need to make sure that Palette 2 can generate filament at its own rate in the printer, but keep up to the average print speed of the printer for most speeds.
I'm done demonstrating how broken and inadequate the Palette 2 buffer system is for now, but Mosaic is pretty good at it too. During the live stream that I snipped the various Mosaic comments from earlier, they were running a print themselves. Let's check out Mosaic's approach for demonstrating the deficiencies of the buffer system.
What I can tell you is that this Maker Gear print right now is printing at 50 millimeters a second.
First, I start by telling that they are printing at a fraction of their claimed maximum speed.
I believe we can go faster than that.
Then,
And
sometime
whether
into the
from
print,
Canvas or
this
a
happened.
separate side app, we will help you upload your firmware.
The
We
buffer
have
runs
every
out,
intention of
but
helping your
two
product
packs
become
save
more
their
powerful
ass.
over time. The filament's not necessarily
Then the
abrasive, but
palette
we
2
did.
finish a
I guess they're
pump
kind of go hand in hand on this.
right
We did
before
a
it starts to splice.
wood fill.
Yeah, we had, we've combined, I know we had Polymaker Polywood. We combined it with a conductive filament called Functionalize F Electric, and we also combine it with bronze fill as well.
Yes.
And those three, the splices looked great. We have a video of them. I'll share the link in the
And
chat
there,
here
the buffer
as
on
well.
Yeah, so we've demonstrated that yes, we can use them, we can splice them. Some people had questions about if they would be strong enough to go through this buffer that we have here. Yes, no problems there. Generally, however, my personal opinion is just abrasive filaments are...
And finally, the filament snapped. Mitch's reaction is priceless. Even though his moral compass might not be fully tuned, his reflexes sure work. He probably would have rather suppressed them this time though. And of course they pretended that nothing had happened until someone called them out in a YouTube comment. You might think that since this was pre-launched they have fixed these bugs by now, but that does definitively not appear to be the case. It might be a bit better at not pairing splices and pongs now, but it still happens, and all the test I did was on the latest available firmware. So what should we conclude from all this? It should be pretty obvious that I'm not very impressed by the work done by the engineers at Mosaic, or by the upper management, or by their marketing department. They designed a buffer that was way too small to begin with, and then they designed a detector system around the buffer that make it impossible to use all of it, and in some cases only a very tiny fraction of it. The buffer empty switch they have chosen is not fit for the task. When the buffer drains, the filament moves almost vertically towards the switch, so choosing a lever type switch was incredibly stupid. A push button would have the force almost perfectly along the axis it was designed for, while a lever type switch will have it almost perfectly perpendicular to that. Something Mosaic first realized when people started reporting jams. The filament would sometimes land perfectly on top of the switch lever and try to push it into the switch rather than tipping it over, and then the whole thing locked up. They then implemented the workaround in software where they slowly jog filament into the buffer even during pongs. This caused the filament to always drag the switch over when ponging, but it does not guarantee a switch activation in a buffer runout situation, so anything clever they might come up with to pause the printer in such a situation would risk failing because the switch never warned the palette about the buffer collapse. I guess they picked the lever type switch to avoid having more entries on their bill of material. Being able to reuse the whole detector module from the filament runout detectors is of course saving them some cost, but given the degradation it gave in functionality as well, I doubt the cost saving they might have gotten from that is enough to defend the poor choice of switch type. So they picked the wrong buffer size, they picked the wrong buffer topology, they picked the wrong buffer switch, and as if that was not enough, they also picked the wrong way to mount the switches. Pretty much all modern electronics use surface mount or SMD components for everything, except one category of component, and that is components that have to resist physical loads, like connectors and switches. If you surface mount those, the only thing preventing them from being pulled off the board is that they are soldered to some tiny 35 micrometer thick cover patches that is glued to a fiberglass board. So for those kind of components, you have to use one that have pins going through the board and that is soldered in from the back. Some types have a few through-hole pins for strength and SMD pins for signals. For the USB port, Mosaic picked a connector that have SMD pins only, so several customers have experienced that they fell off due to stress induced by the cable. For the switches, they picked a hybrid component with through-hole for strength and SMD for signal, but then they decided to specify non-plated holes and no solder pads for the through-hole pins, so they are not soldered at all and provide very little physical strength. So several customers have had them fall off too. So pretty much all engineering on the Palette 2 is really shabby work. And then you have all the lies in their advertisement and how they lie, smokescreen and dodge in response to any question asked about the actual performance of the machine and its accessories. That is seriously disgusting and pisses me off a lot. So they have a lot of negative going for them, but the concept is so unfracking fantastically cool. And as long as their only real competitor is tied to printers of a single brand, the Palette 2 still have some appeal, even though their implementation of the concept is utter crap. A lot of people willingly or unwillingly and sometimes even unknowingly comply with the limits it have and are making very beautiful prints. Unknowingly because they don't realize that even though they type 80 mm per second into their slicer, that does not always mean the printer is actually able to reach that speed. Some printers will have a cap, and no printer have infinite acceleration or deceleration. So for small complex objects, the actual speed often have nothing to do with the speed numbers you gave the slicer, but is entirely defined by the allowed acceleration. And then you have people like me that design things like the external buffer to patch up some of the horribleness. With it, I'm able to get its performance at least slightly past the pain limit that I'm willing to endure. And I'm so hooked on the ability to use water-soluble support for my complex prints that if my palette got stolen tomorrow, I would sure miss it despite all its shortcomings. In such a case, I would look really hard into alternatives, but in the end, I might have ended up buying it again. But I would keep bitching about all its brain-dead design flaws, of course. Mosaic should cross their fingers and hope they will keep the monopoly until they grow up though. A serious competitor, and my prediction is that this thing will be history in a jiffy.